Alright, in this video, I'm going to go over the linear regressions. And that's the most the the basic the concept used in machine learning. So let's take a look at the question. How can you learn to predict the prices of houses as a function of the size of their living areas? So if you want to predict the house price um, as a function of size of the living area, but not only the living area, but there's a number of bedroom and number of bathroom and school zone and neighbors, so and so on. So the price of house is output variable, what we want to predict, and the size of the living area can be considered as input variable. So before the starting, we need to the set notation for input variable, output variable, and other uh, the parameters. So x superscript I represent the ith input variable. So the input variable is called the feature as well in computer science, and y superscript I represent the ith output variable or target variable. Okay, so target variable means the variable we want to predict. Okay, and x superscript I comma y superscript I, that the order pair is called the ith training example. Okay, so as you may the expected, we gonna collect the maybe hundreds or thousands the training examples, and then we put a label for each training example. Okay, so this is ith training example. So that means training example means that we're gonna use this one as to build a function whose output is the the feature, a target variable. Okay, value of target variable. So training set is a set of all the training example. Okay, so here m, keep in mind is m is the number of training example. Okay, so training set is what the data set that we will be using to learn and predict other houses price. Okay, so the script x, capital script x represent the space of input variables, input values, and the script y represent the space of alpha values. But in this the problem, the input value and output value is a house price, which is number, right? And the input value is also a number of living area or number of bathroom, something like this should be the number. So in these problems, both must be a real number. Okay, the set of all real number. Okay, so yeah, right here. So let me give an example. Living area is put a unit square feet. So x superscript I1 is 2,104 square feet. So that's a living area. Okay, that's the number in the first training example. Okay, and then this is house price corresponding to that living area. Okay, so and so on. You see that? So you see that superscript represent what the index of training example. Keep in mind that, and then 1, 2, 3, and so on up to what m, right? Because we see that I told you the m is what the total number of training examples. So we have m training examples, and the superscript represent the index of training example. Keep in mind that. Now the goal, given a training set, our goal is to learn a function h. H is function mapping from x to y, such that h of x is a good predictor for the corresponding value of y. Okay, so h of x is called the hypothesis. Okay, so now we want to design the hypothesis. Okay, so for given training set. Okay, training set is what, for example, ith training example, see x superscript I and the subscript 1 up to the n features. Okay, so subscript is what? The index of features. What that means, the subscript 1 maybe represent the living area, and the subscript 2 maybe represent number of bedroom. Subscript J maybe represent the school zone number. Okay, school zone number, something like this. Okay, so there are n features. Right? Okay, and this is ith training example. Okay, so you need to clearly understand the meaning of superscript and subscript. Okay, that's quite uh, the quite important. Otherwise, you may get confused. So superscript is told you the index of training example. Okay, and then subscript represent the index of feature. If you just express the all the training examples in matrix, then the uh, the uh, the subscript J represent index of column, and then superscript I represent index of row. Okay, so for each I we get the n plus 1 columns in a matrix when we express the training set. Okay, then the matrix will be the n by n size matrix. Okay, and then but we don't include the target variable as input uh, the as input of the h of x. So here so we get the that's why we get the n by n matrix. Okay, not n by n plus 1. No. Alright, so now the learning algorithm, yeah, we design a learning algorithm. We're gonna learn this one later, okay, soon. And finally, we get once we build up H, then we put the features of a certain house, what we don't know the house price, okay, and then we get the prediction of the house, the price of that house. Okay, so we call the learning problem a regression problem if y is in a set of real number. Okay, and then classification problem is what if y is in finite discrete set. Okay, so it means that y can be only 0 and 1 or 1 and 2, something like this. So now let's see. Excuse me, linear regression. To make our housing example more interesting, let's consider a slightly richer data set. Yeah, so we saw that before. So we're gonna put more the features. So let's say subscript 1 represent the size of house, subscript 2 represent number of bedrooms, subscript 3 represent number of bathrooms, something like this. Okay, expressing this one as matrix, we get this. Okay, so x11 represent the input value in the first training example. Okay, so first row vector represent first training example. Okay, and first column represent the first feature. Okay, input values of first feature. Okay, so x11 represent what the size of house in the first first training example. Okay, so now xij, then what? Xi, the subscript I represent ith training example, j represent the jth feature. Okay, so now then how can you design the hypothesis h? Yeah, that's the main part of this video. So we approximate y as a linear function of x. Okay, so x is not a single number, x is a column vector. Okay, because what's the input now here? So you see that the input is that's the row vector is input value of the hypothesis. Okay, but we're gonna transpose the first row to make the column vector. So the x is a column vector. Okay, so now then we approximate y by hypothesis h. So we can say h is the approximation of y. Right? And then we define h as a linear function. We see that here, linear function. And then let's consider that we have we set only we consider only two features. So that's why we got x1 and x2. Okay, subscript 1, subscript 2. That means this is the first feature, the second feature. Okay, we assume that only we consider only two features. Okay, theta 0, theta 1, theta 2, these are the coefficient. Okay, or we can say parameters, or we can say weight of linear regression. That's what we need to figure out. Okay, anyway, so we can express this one as the matrix multiplication, or we can say dot product, right? So this can be expressed as a theta transpose of theta times x. Keep in mind this. What is x? X is a column vector. This is this 1, x1, x2. Okay. So so x1 is representing the first feature, x2 is the second feature, right? So for n features, then h of x hypothesis can be expressed as like this, right? This makes sense, right? Because considering x naught is 1. You see that here, we don't have x naught, but you know, saying that x naught is 1, then we can say x is 1, x1, x2, right? All right, so here's the example. The h of x superscript 1, what does it mean superscript 1? This is the first training example. So we input first training example into hypothesis, then we got this. Is it? Okay. So this is approximation of the first target value, right? Okay. So we determine theta so that this is really close to superscript 1. Okay, really close. We want to get the value of h, which is really close to the first target value, right? So we make h of x close to y, at least for the training examples. Yeah. So we have we define the cost function first. What the cost function like this, which means the difference between the hypothesis and the target value in the training example. What we already know, and take a square, and then sum of them, and then divide by 2. Okay, that is the cost function. Okay, so and then what are you gonna do? We wanna minimize. We wanna find the theta that minimizes that cost function. Okay, so j of theta, it means that I already told you, but it means that j of theta measures how close the hypothesis are to the corresponding the y superscript I, which is our target value of training example for each theta. Okay, so now before figuring out how to find theta, then minimize cost function, let's just let me just go over this one in detail. Okay, so j of theta is expanding the sigma. Then j of theta can be expressed as like this. You see that here. And then h of xi is what actually can be expressed as a sigma theta j xj. On the superscript 1, superscript 2, which means the first training example, second training example, and so on up to the mth training example, right? And then each sigma can be expressed as a vector multiplication, theta transpose times x, right? Okay. So now then, that's too much, right? Too many of the training examples, but it be reduced m to 3, okay, and they also reduced the number of features to 1, okay. So then we can plot the each terms like this. Okay, so let's say here a horizontal axis represent feature, the vertical axis represent the what difference between the hypothesis and then target value. Then since we have since we consider only one feature, that's why we got only one horizontal axis, okay. Okay, so if you have a two feature, n is 2, then we're gonna two features, so we get the maybe 3 axes, right? Okay, so now then and then see m is 3, so it means that we have 3 training example. So we say 1, 2, 3. Okay, and see each values represent the the input values of uh, the the feature, one feature. Okay, for each training example, right? First, second, third. So for each input value, we're gonna let's say this line is the graph of h of hypothesis. Okay, and then this gonna be see that is the actually this is a point of the order pair of the input value and the output value, which is target value, right? For the first training example, the second training example, and third training example. Okay, and then the difference between the point to the line represent what? Difference between the hypothesis, the value output of hypothesis as input of this one, and that the actual the target value, right? Okay. So it means that this is theta transpose times x superscript 1 minus y superscript 1. Does it make sense, right? Okay. So now then what are you going to do? So the determining theta means that we want to find the best line that minimize that these sum of these distance. Okay. That's the the meaning of the j of theta, the cost function in linear regression, and then that's what we have to do. So we want to determine theta that minimize the distance, sum of the distance, sum of square of this distance. Okay. So we want to choose the theta so as to minimize j of theta. Yeah. So how can I do that? So now the problem turns out to be minimization problem. Okay. So then we're gonna use the gradient descent algorithm. Okay, so I'm gonna talk about this one in another video, but just take a look at this. So what's gradient descent algorithm? So theta j, we update the theta by following that formulas. Okay, so let's figure out what that means. Gradient descent algorithm in a linear regression. Okay, so when m is 3 and n is 1, then j of theta can be expressed as like this. Like this, right? Okay, so but only considering because we only consider n is 1. So okay, so now then this one we only consider the first training example. Okay, so then j of theta gonna be like this, and then the expanding h of x superscript 1, then we get this, right? Okay. So now then this is theta 0, theta 1. These are unknown parameters. Okay. So m equals 3 and n equals 1. We j of theta can be considered as a function of theta 0 and theta 1. So it means that j of theta is what two variables. This is a multivariable function, but two variables, theta 0 and theta 1. Okay. Okay. So now then let me just drop this superscript 1. Okay. So to make it simple. Okay. So then this is what actually this is the quadratic equation for theta 0 and theta 1. So we know at which point this one has a minimum value at vertex point in a quadratic, because this is a quadratic equation. Okay, so if you review j of theta as a function of theta 0, then we're gonna get quadratic parabola like this, and then horizontal axis is theta 0. And then we see that here at the vertex point, the j of theta gonna have a minimum value. Whereas here, when you view j of theta as a function of theta 1, then well, we get the minimum value of j of theta at that point, right? Okay. So now we at this point, what the slope of tangent line, which means the derivative of the cos function with respect to theta 0 and theta 1 respectively equals 0. Is it? So the writing it mathematically, then we got this. It's not a big deal, right? So we take a derivative of j, partial derivative, right? So take a partial derivative of j with respect to theta 0 and theta 1, then we're gonna get this, and this should be 0, right? Because slope tangent line is 0 at these two vertex points. Okay. So let's say theta 0 hat and theta 1 hat are the x coordinates of at the vertex point. Then at theta 0 is theta 0 1, at theta 0 hat and theta 1 is theta 1 hat. These two the equation must be true, satisfied, I mean. Okay. So now then, let's see. Now we we go back to the gradient descent algorithm. So theta 0 nu equals theta 0 alt minus alpha this partial derivative, right? Theta 0 theta over partial theta 0. Okay, so now then, you see that here, this is the, we apply the gradient descent algorithm at j equals 0. What was j? What was j? J is the index of feature. Okay, so this is 0th feature. We apply the gradient descent algorithm to update theta sub 0 old. Okay, so now then we figured out what it is. This is what? This one, right? See that right there? You see that? Okay, we'll just copy this one in right here. Okay, now then rearrange this one like this. Okay, so I just take out the negative sign out of the parenthesis, and then we got positive sign right here. Okay, and actually this is what h of hypothesis h of x. So we got this. Similarly, theta for j equals 1, I mean the first feature, theta 1 u can be expressed as like this: y minus h of x times x1. So in general, with a single training example, partial derivative of the cos function with respect to theta j can be expressed as like this: h of x minus y times x sub j. So in a linear regression problem, the gradient descent algorithm can be is equivalent to this: theta plus alpha y minus h of x xj. Okay, so what that means? So it means that, you see, this rule is called the least mean square LMS update rule, and is also known as the video half learning rule. Okay, so the property of LMS is this: you see the magnitude of the update, which means that the difference between theta z new and theta z old is proportional to this one. Okay, to the see the error. Actually, y minus h of x is error, right? Okay, so it means that if the y minus h of x is large, then a large change to the alpha should be made. It makes sense, right? Okay. So now then, what that means? Is it large? That means that what? Theta u must be the what? I mean, we need to the significantly update the theta z if this error is large. That's why we have to put more the higher number, certain higher number to alpha. Okay, but normally alpha is set to between 0 and 1. Okay, all right. So there are two ways to update the parameter theta z. Okay, so it means that there are several ways to apply the gradient descent method. First one is SGD, stochastic. It stands for stochastic gradient descent. So for I goes 1 through m, that means the I is an iteration of the training example, and then for j goes 0 to n in the iteration of feature. Okay, so it means that what? The parameters are being updated even after one iteration, in which only a single example has been processed. It makes sense, right? So for first single iteration of the training example, the all of features will be updated. Does it make sense, right? Okay. So okay. So then what? Yeah, there is a pros and cons this one. Let me talk about this one after introducing batch gradient descent. So batch gradient descent is called in short, it's called the BGD. So this is slightly different. For j equals 0 n, theta j equals theta j plus alpha. So now then, you see the sigma right there? Just take a look at difference between the SGD and then BGD. So theta j is updated per the iteration of one iteration of feature. The theta j is updated by sum of the difference of y and h from 1 to I equals 1 to m. So the BGD takes the sum of all the training sets. M is what? The number of training example, right? So to update every single feature of the theta j, we use whole the training examples. So the BGD takes the sum of all the training set to run as single iterations. So you can see that this is gonna take time a lot to update the data, J, right? Rather than this. So here's the pros and cons of SGD and BGD. So SGD is faster. Why? Because look at this. So to update the data J, we just calculate the what the difference, I mean the error of the ith training example. But here we can compute the error of ith training example, but I equals 1 through m. So which one is faster than the other one? Yeah, that's the SGD must be faster than the BGD, is it? So SGD must be faster. This is slow, but less computational expensive. Yeah, and then that lead to faster and slow. They lead to the computationally expensive, right? And they can be used for SGD. It can be used for large training example. Okay, and the BGD not suggest for large training example. Yep, makes sense. And the SGD give good solution but not optimal. It means that SGD is unstable because data J is updated um, for only one single to update data J. Only one training example is used. So maybe SGD is fast, right? But SGD is kind of unstable to find the optimal, I mean, global minimization. Okay, so BGD is give optimal solution. Okay, and then the sample should be in a random order. It means that we have to shuffle the training example, but BGD not random shuffling is required. So, but the third one, mini batch gradient descent, that's the faster than both SGD and BGD. Okay, so to the overcome the drawback of the BGD, okay, but having the all the pros on SGD, we developed the new kind of gradient descent method. It's called the mini batch gradient descent. It means that we the introduce one more variable. Okay, b is number of example, but less than total number of a training example. Okay, so for before the what here we see. Yep. So now for I goes 1 through b, and j goes 0 through n. Data j, you see that right there. See, this is different from the that's the that's different from the BGD. So before we take a sum of all the errors, but we only take a sum, partial sum from I to I plus b minus 1. Okay, so when we update the parameter data j by taking not whole sum of the errors but partial sum. Okay, that's the difference between a mini batch gradient descent and batch gradient descent. So it this one that the B The what's the ultimate value be, that all depends on application, but this one, this mini batch gradient descent must be faster than the BGD, and then more stable than the SGD. Okay, yep, that's for today.